Note that we just talked that P of H greater than equal to 0, but you know that probability, initially we defined probability is a function from C to R, it is a real number, but you know that it is not only real number, it is actually it is 0 to 1 only, probability always between 0 to 1, but initially we just talk about it is nothing but C to R. For any A, P of A is a real number, but one by one we gave the axiom. So, axiom 1 says that P is greater than equal to 0, it is a positive real number including 0 greater than equal to 0, P of AC is equal to 1, but you know that for impossible event P of phi is 0, but here we did not mention. P of A greater than equal to 0 we mentioned, but P of A less than equal to 1 we did not mention in the axiom. Also third, union of I is equal to 1 to infinity, this probability is nothing but sum of I is equal to 1 to infinity probability of AI. So, this is axiom 1, axiom 2 and axiom 3. In particular we discussed it is given probability of A1 plus probability of A2. So, there are many other things we use in probability, that if A is subset of B, then probability of A is less than equal to probability of B, and we know that it is a kind of notation, all the element in B which is not element in A, B minus A, this is nothing but probability of B minus probability of A if A is a subset of B. So, those properties, so P of phi is 0, P of A is less than equal to 1, those properties we have to prove because it is not in the axioms. So, those properties in the future we will use frequently, that because it is probability. So, that means A is a subset of B, then probability of A is less than equal to probability of B. What about probability of A complement? It is nothing but probability of A 1 minus A PA. So, those who have already learned some probability, basic probability, we frequently for computing probability numerical problem you use this kind of results. So, those results it is neither in the axioms nor we have proved, we cannot use that because we do not know it is true or false. So, whenever we prove it, then only we can use it. So, if it is in the axiom, you can directly use it because by this axiom it satisfies, then only it is probability. So, if we say P is a probability, then it must satisfy all these axiom 1, 2 and 3. For any other property, if you want to use in the future, we have to prove it. So, some of the important theorems or results we will prove in the here. So, some of the important theorems, because all those theorems in the future we frequently use it. So, it is important that we should know that it is really correct. So, we have to prove it first. Let us discuss this theorem, first theorem, theorem 1.1. If A1 is a subset of A2, then probability of A1 is less than equal to probability of A2 and probability of A2 minus A1, this notation should be like this, it is a forward slash A2 minus A1. So, this should be probability of A2. So, in a set theory it is not the real number 3 minus 2 equal to 1, it is a set A2 minus A1 means all element in A2 those does not belongs to in A1. So, this is nothing but probability of A2 minus probability of A1. So, this is the if A1, if this satisfying under this condition. So, let us prove this theorem first. So, it says that theorem 1.1, if A1 is a subset of A2, probability of A1 is less than equal to probability of A2 and probability of A2 minus A1, this is equal to probability of A2 minus probability of A1. So, let us prove this. So, first of all let us write down what is A2 minus A1. Suppose this is a sample space S, this is A2 and A1 has to be subset of A2. So, this is A1. Now, A2 minus A1 means this set. So, this set can be represented by A2 minus A1 can be represented by A2 intersection A1 complement, because A2 intersection. So, if you intersect with A2, the common element of A1 complement will be containing all this set. So, all the element in S which does not belongs to an element of A1. So, if you take intersection of A1 with A2, so this is nothing but A2 minus A1 complement. Now, this A2 minus A1. So, this set A1 or this set A2 can be written as disjoint union of A1 union A2 minus A1. So, this joint union of, suppose this is A1 and these are the A2 minus A1 this. So, suppose this set is B1 and this set is B2. So, then B1 union B2 is equal to A2. Not only that, B1 intersection B2 is phi. So, we consider here B1 is equal to A1 and B2 is equal to A2 minus A1. For simplicity, we are just taking this notation. So, now we can see that B1 intersection B2 is a null set. Now, just Venn diagram very quickly we understood it, for that is why we wrote it. For set theory also you can show that if S belongs to the left hand side, then this belongs to this. This is also null set, you can show that, because B1 is nothing but the set A1 and B2 is nothing but all the element which does not belongs to A1 but A2. So, that is why these are disjoint. So, now using axiom 3, using axiom 3, we know that because B1 and B2 union B2, because B1 and B2 are null set. So, probability of B1 plus probability of B2. So, which implies B1 and B2 is equal to A2. So, probability of A2, this is nothing but probability of B1 is nothing but B1 is A1, probability of A1. So, here we can write, since B1 intersection B2 is null set. So, this is by axiom 3 it is required. Now, probability of B1 is A1 plus probability of B2 is probability of A2 minus A1, which implies here we are getting probability of A2 minus A1 is nothing but probability of A2 minus probability of A1. So, this is the first result, A1 subset of A2, probability of A1 less than equal to probability of A2. This is the theorem actually, A1 subset of A2, then this. Now, next we have to prove that probability of A2, this result we have proved, this result, probability A2 minus A1 is probability of A2 minus probability of A1, we have proved it. But we did not prove this result, probability of A1 will be less than equal to probability of A2. So, now this is probability of A2 minus probability of A1, we found that probability of A2 minus A1. Now, by axiom 1, for any event A2 minus A1 also event, because A2 minus A1 you can write A2 complement A1 A2 intersection A1 complement. So, it is a event. So, this is greater than equal to 0 by axiom 1. So, you can see that what axiom 1 says. Axiom 1 says that probability of A should be greater than equal to 0 for any event A. So, A is, because all the other set these elements are, so because A2 also belongs to C, A1 also belongs to C, because they are event we are talking, A2 intersection A1 complement also will be in C, so it will be event. So, that is why this will be greater than equal to 0. So, from that, because probability of A2 minus probability of A1 is greater than equal to 0, we see that probability of A2 is greater than equal to probability of A1. So, this is the proof of this theorem 1. This proof is not very complicated or difficult, but till we need to prove it, because in the future we will write down, we will use this theorem. So, we need to know that we frequently use it. A is a subset of B, so probability of A less than equal to probability of B, and probability of B minus A is equal to probability of B minus probability of A. Whenever A is a subset of B, if A is not a subset of B, we cannot use this result. So, that is why it is important. Now, theorem 1.2 says that for every event A, probability of A will be greater than equal to 0, less than equal to 1. Now, in the axiom 3, we have already axiom 1, we already know that probability of A is greater than equal to 0, but less than equal to 1 we do not know, that we have to prove it. So, let us prove here. So, theorem 2 1.2, for any A belongs to C, that means A is a subset of S, any event actually, probability of A is less than equal to 1, greater than equal to 0. By axiom 1, probability of A is greater than equal to 0. Now, we have to prove that probability of A is less than equal to 1. How we can prove that? So, since A is a subset of S, which implies probability of A is less than equal to probability of S. This is by, so we have already proved this, that is why we can use here by theorem 1.1. Now, which implies probability of A is less than equal to 1, since this is the PS using axiom 2. Axiom 2 says that PS is equal to 1. So now if you hence combining these two, PA is less than equal to 1, greater than equal to 0. So, these are very straightforward proof. So, next theorem says that theorem 1.3, for empty set P of phi is equal to 0, because in the axiom we did not mention that. So, we have to prove it. So, theorem 1.3, for phi, because since it is belongs to C also, so it is not needed. For phi it is a event, P of phi is equal to 0. So, P of phi is equal to 0, but phi already in the C. So, now because S complement in C, so P of phi is equal to 0, how we can prove that? So, now if you consider S and phi, two events, S intersection phi is nothing but phi, from by axiom 3, probability of S union phi, this is equal to probability of S plus probability of phi. Now, in the left hand side it is nothing but S, this is equal to probability of S plus probability of phi. Probability of S we already know, this is 1, this is 1 plus probability of phi, which implies probability of phi is equal to 0. So, these are very straightforward, but we want to prove, because without proof we may not be use it, it may not be used for further in the whenever we will use this, we need to prove this. So, now the another theorem 1.4, for any A complement, A is a event, for any event complement of A, probability of A complement. So, sometimes A complement is nothing but, if it is the S, A is the event. So, this is A, this is S. Now, A complement is there all the element which does not belongs to S. So, this is the A complement. Now, sometimes we denote A dash, A bar, A complement, it is just a notations. This is defined by all element S such that S does not belongs to A. This is the notation. Now, for suppose if you use A dash, it is theorem 1.4 says that probability of A dash, A complement is nothing but 1 minus probability of A dash, A complement. So, how to prove that? So, we can use this relation because A union A complement is nothing but S, also A intersection A complement is phi. So, using axiom 3 P of A union A complement, this is nothing but probability of A plus probability of A complement by axiom 3, because they are disjoint, which imply probability of A union A complement is S. This is nothing but probability of A plus probability of A complement, which implies probability of A complement is equal to, so P of S is equal to 1. So, Ps minus probability of Pa, this is nothing but 1 minus probability of A. So, okay, actually it is a typo, sorry, it is a mistake. Probability of A dash is equal to 1 minus probability of A. So, this is theorem 1.4. Now, theorem 1.5 says 5. So, theorem 1.5 says that for a finite mutually exclusive events, finite number of, suppose A1, A2, An are pairwise mutually exclusive event, we can write probability of A1 union A2 union An, this is equal to probability of A1 plus probability of A2 plus probability of An. It seems that it is very obvious from the axiom 3. Axiom 3 already it is mentioned for the infinite number of events, but till if it is mentioned for infinite and 2 events also it is meant. So, we need to prove it from the infinite, for finite case also it will be true, you have to prove it. So, first let us prove this. So, theorem 1.5 says that let A1, A2, An be a collection of pairwise mutually exclusive set of events. Then probability of A1 union A2 union An, this is denoted as A actually here, probability of A1 plus probability of A2 plus probability of An. For any finite, suppose infinite it is given, so then we have to prove that finite, any finite union also it will satisfy, because they are mutually exclusive. Let us consider Bi is equal to Ai for I is equal to 1 to n, and B I is equal to null set for I is equal to n plus 1, n plus 2, like this. Hence, we have a infinite collection, or and they are pairwise mutually exclusive also. So, this is actually countably infinite pairwise mutually exclusive set of events. So, why they are pairwise mutually exclusive? Because if you consider any I not equal to j bi intersection bj, I not equal to bi intersection bj, if ij are both less than equal to n, because they are a1 a2 n are pairwise mutually exclusive, so ai intersection aj will be phi. For any of the I or j it is greater than n, then one of the will be bi or bj will be phi, and then intersection will be phi. So, they are mutually pairwise mutually exclusive events. So, pairwise mutually exclusive events. Hence, using axiom 3, probability of B1 union B2. So, let us write down in the next page. So, using axiom 3, so probability that B1 union B2 union like this infinite collection, this will be summation of. So, let us write like this, probability of B1, probability of B2. So, we can write union Bn, union like this, plus Bn plus Bn plus 1 like this. So, note that up to B1, B2, Bn it is nothing but A1, A2, An, and the more than n be nothing but phi implies. This is equal to here also P of A1, because here infinite collection B1, B2, Bn infinite collection. So, we can apply axiom 3 here. So, by axiom 3 this union this is equal to this, and then we are replacing their representation like A1, probability of A1 plus probability of A2 plus probability of An plus probability of An plus Bn plus 1 become phi, probability of phi plus probability of phi, like this. So, the left hand side union of with the phi, it is nothing but probability of A1, probability of A2, union An. So, with union with phi will be the same set, and the right hand side it will be probability of A1 plus probability of A2 plus probability of An, and the remaining will be all zeros, 0 plus 0 plus 0. So, that is why we proved this result for finite case also. So, this is proved. Now, this is that is why we can, like in the axiom 3 we have used for 2 events. So, it is not required, axiom 3 actually infinite events we can only write. So, then this finite case we have proved here only. So, then we can say that it is true for finite cases also, but here we written in particular for finite 2 disjoint sets also, probability of A1 union probability of N1 U2 equal to probability of A1 plus probability of A2, but we have proved in theorem 1.5. So, next important result is that for any 2 events A and B. So, A and B are, if they are disjoint, suppose if A and B disjoint, if A and B are 2 events, that means it is in this C, such that A intersection B is equal to phi. Then by axiom 3 also in theorem 1 point here what is the theorem 1.5, this is for finite cases also probability of A union B will be probability of A plus probability of B, because this can be because they are disjoint. Now, if they are not disjoint for any event, for any 2 events A and B which may be disjoint or may not be disjoint. So, any 2 events A and B. So, that means A B belongs to C, this collection. Probability of A union B. So, because it is a sigma field, A union B also will be in sigma field. So, it will be again a event. This is nothing but probability of A plus probability of B minus probability of A intersection B. This is the theorem. So, this is one of the important theorem, you know that addition of 2 events. So, it may be disjoint. So, if it is disjoint, then probability of A intersection B will be phi, probability of phi is 0. So, in that case this will be true, probability of A union B equal to probability of A plus probability of B. But if in general cases, how we can prove it? So, suppose if you use a Venn diagram, so suppose this is A and this is B. So, this is the sample space S, this is the set A, this is the set A, and this is the set B. So, then this set is nothing but A intersection B. Now, if you add probability of A, so this is the probability of A, and then with adding with probability of B, then you can see that A intersection B you are adding 2 times. So, that is why one A intersection B we have to subtract to get the probability of A union B. Now, we will prove it analytically also, Venn diagram it may not be exactly, it may not be, we may not get the clarity, just it is just a graphically we are representing how to prove analytically. So, A union B. So, let us again take the help of this. So, suppose this is S, this is A, this is B, this is A intersection B. Now, this A union B, if we want to represent A union B as a, sorry, okay. Sorry, this is S, this is A, actually I want to make it S, then this is A and this is B. So, then we got that this is S, this is the event A, this is the B, this is A intersection B. Suppose you want to find the A union B, we want to represent in a 3 different disjoint sets, union of a 3 different union sets. So, one set is like this, another set is like this, and another set is this. So, this set can be represented as A minus A intersection B, this set nothing but the A intersection B, and this set is nothing but B minus A intersection B. So, this is we denote as C1, this is we denote as C2, this is we denote as C3. So, A union B, it can be represented as C1 union C2 union C3, where C1 is nothing but A minus A intersection B, C2 is A intersection B, and C3 is B minus A intersection B. C3 is B minus A intersection B. Now, C1 is A minus A intersection B, C2 is A minus A intersection B, C3 is B minus intersection B. You can easily show that C1, C2, C3 are mutually exclusive events, because C1 and C2, C1 defined by all element A which are not in A intersection B, and C2 is exactly that A intersection B. So, this will be disjoint. Similarly, C3, C2 also will be disjoint, and also C1, C3 will be disjoint. So, this can be because common part is A intersection B, we are considering all element in C1 which is not in A intersection B, and C3 is all element in B which is not inside A intersection B. So, C1, C3 also will be disjoint, that can be very easily shown. And also C1 union C2 union C3 can be shown that it can be, it will be the A union B. So, these are disjoint. So, Ci intersection Cj is phi for I not equal to j. So, using theorem 1.5. So, theorem 1.5 actually this finite disjoint a pairwise mutually exclusive event, we can have this result. Probability of A union B is probability of C1 union C2 union C3, because by using theorem 1.5 this is probability of C1 plus probability of C2 plus probability of C3. Now, what is probability of C1? Probability of C1 is nothing but A minus A intersection B plus probability of C2 is probability of A intersection B plus probability of C3 is B minus A intersection B. So, which is equal to, now we apply the theorem 1.1. So, A intersection B is a subset of A. So, it is nothing but probability of A minus probability of A intersection B. It is as it is probability of A intersection B plus probability of B minus probability of A intersection B. This is using theorem 1.1. Now, we just simplify it, this probability of A intersection B and probability of A intersection B cancelled. So, then finally, we got this is probability of A plus probability of B minus probability of A intersection B. So, this is one of the important result. So, there are many applications to find the probability, suppose A and B probability and A intersection B probability known, then we can find the probability of A union B.